Hi, my name is Nick Generakis, and today I will talk about the design of an intermediate language to simplify the development of network analysis. This is joint work with Devon Lair, Ryan Beckett, and David Walker. Skimming through the news, you will find that network errors are notoriously common and extremely disruptive. Major incidents that cause blackouts for a large portion of the internet happen far too often. And if you read those articles more carefully, you will find that often these outages are caused by human errors and misconfigurations. To understand why it's difficult to correctly configure a network, let's look at how they function. In this work, we focus on the network's control plane, which is the component that is responsible for computing the paths over which routers can communicate with each other. Given the routing devices, operators will issue configuration files for each device, selecting the routing protocols they should execute and tweaking various parameters to control the routing policy. Now the devices will start executing these protocols and exchange routing information with one another until the system converges to a stable state where every device has learned of a preferred set of routes. And as with all distributed systems, you can imagine why correctly configuring the control plane can get tricky. In particular, unlike our previous network with 4 devices, modern data centers have thousands of devices that need to be configured. And moreover, the configuration should enforce the right routing policy even when some devices fail, which is bound to happen when you have so many of them. The last row is the actual configurations. It's not unheard of for configuration files for a single router to consist of several thousand lines of commands that are written in very low-level vendor-specific languages. These languages use domain-specific ad hoc commands that work for specific routing protocols and features, and they lack intuitive semantics, especially when considering their interaction with each other. Moreover, the configurations only control some aspects of the routing behavior. Other aspects, such as how each protocol compares two routes, are implicit and are part of an RFC or the router's firmware implementation. So, between ad hoc constructs and implicit semantics, it requires very good familiarity with these protocols in order to understand them and to be able to write these configurations. We have a challenging verification problem on hand, and it has attracted interest from the programming languages and verification communities, yet it takes a lot of effort for them to make breakthroughs in control plane verification. To understand why, let's look at the research and development cycle for verification tools. Typically, one will sketch their idea on paper and refine it until it's time to implement an initial prototype and actually try it out and see how it performs. It might perform really well, in which case the problem solved, or they might need to go back to the whiteboard and refine their idea and refine their implementation. But in the case of networks, the problem is that you sketch your idea, and then when you try to implement something, you realize that there is a bunch of different protocols, like BGP and OSPF and RIP and so on, and a bunch of different vendor configuration languages, and you end up spending a really long time just to get an initial prototype going, which is very discouraging. With my co-authors, some of whom have developed a number of these tools and finally had enough of that, we asked, what can we do to simplify the research cycle for network verification tools? The answer to that question is to build more abstractions. At a very high level, a distributed routing system can be described by a routing algebra, which consists of a topology, a set of nodes and edges between them, and an algebra, which consists of a set of routes. This is the information that the distributed system computes. A merge function, which describes how routers combine routing information from two different neighbors. A transfer function that describes how a route is transformed as it traverses each edge on the network. And finally, an initialization function that provides the initial routes announced by each node. In this work, our goal was to design a practical language to build instances of routing algebras, and in particular, a language that can act as an intermediate representation to support the task of building verification tools for real router configurations. This means that the language must offer the features necessary to model the configurations at an abstraction level that is useful for verification, but at the same time, it should exclude features that are not necessary and will make verification very expensive. So the intermediate representation should allow us to completely separate the tasks of one, developing models of protocols, and two, developing analysis. When developing models, we have to translate the vendor configurations into this representation, and we have to think about how BGP and OSPF and all of these protocols work, but we don't have to worry about how to efficiently simulate them or how to represent these protocols as SMT constraints. And on the other hand, when we're developing analysis, we don't want to be bugged about the different source languages and different protocols and how they interact and so on. With these goals in mind, we chose a design that revolves around a standard functional language with conventional and well-understood programming constructs such as options, records, functions, and so on. These constructs are expressive and compositional, which allows us to build complicated routing algebras from simpler ones. And this is also something that helps keep the size of the language down. Another aspect that facilitates our goals with MV is that an MV program describes all behaviors of the routing protocol in a high-level language, which makes routing systems more accessible to broader audiences, such as formal methods people. In this example, we define an idealized version of BGP, and you can see all the components of the routing algebras. First, we define the type of message exchanged, in this case an option of a record with 3 commonly used BGP fields. Then the topology, which is described by a very basic language, and then you can define as many helper functions as you want, but eventually you need to define a transfer, a merge, and an init function that capture the essence of a routing algebra. Most of the language is deliberately simple and standard, so I won't go through this example in detail. But one aspect of the language that I want to focus on is finite maps, because it turned out to be quite important for modeling and analyzing networks, and let me show you why through some examples. Let's take a look at what happens in this network, which is based on a commonly used data center topology called FAT-tree. Every top-of-rack router announces a route towards a destination, and these destinations are represented by IP prefixes. Then these routes are propagated throughout the network. And this is exactly what a network simulator does. It computes the routes for every node in the network by simply mimicking the way the actual control plane works. Nodes exchange routing information with their neighbors until a stable state where every router has picked the best routes available to it is reached. In terms of routing algebras, the routing information exchanged in this example are maps from destination prefixes to BGP routes. Notice here that for the map computed by the spine routers, there is a lot of redundancy. Basically, the routes towards all destinations are the same. So a naive implementation of maps will not scale very well, as these data centers have hundreds or even thousands of destinations. So our implementation of maps leverages this redundancy by using multi-terminal binary decision diagrams and compactly represents the map. I gave you one example of why smart representation for maps is useful, but there is a more general observation to be made, and that is that networks tend to have very uniform designs because it makes it easier to configure them and extend them. Hence, there are many opportunities to exploit symmetries in our models, as also noted by prior work. To expand on this, now consider the case where we have a single destination in the network, and we want to reason about the routes compared when any two links can fail. Let's look at what happens to the routes of a specific top-of-rack router, which we will call T1. Doing this naively, we have to enumerate all possible two-link failure combinations. But notice that because of the design of the network, most of these failures do not affect the route selected by T1. In fact, the only two combinations that matter in the case of T1 is the failure of the two links that lie on T1 or of the two links that connect the destination to the rest of the network. So like before, we can compactly represent T1 routes under different failure scenarios using multi-terminal BDDs. And I want to stress that besides the memory savings, the advantage is that when T1 propagates the map it has computed to its neighbors, it only has to process these two distinct routes. We evaluated the performance of our simulator using synthetic data center networks that were running BGP with shortest path policy, plus using some tags to disallow some backup routes. And the networks were between 500 and 1,280 nodes, and announced between 200 and 512 prefixes. So we compared our simulator with BATFIS, which is a state-of-the-art network simulator. And the thing I want to focus on is the advantage of using multi-terminal BDDs to represent the routes for each node. Simulation time more than doubles or even triples for BATFIS with every increase in the network size, while for MV the scaling trends are much smoother, and that's because adding more destinations has less impact because of their compact representation. So comparing the simulation time for the first network that announced 200 destinations and the third one that announced 392 destinations, you can see, and this is the largest network that BATFIS actually could simulate before running out of memory. You can see that for MV simulation time increased by a factor of 3, while for BATFIS simulation time increased by a factor of 8. And similar trends, maybe to a smaller degree, are visible when you look at the memory consumption of the two. For fault tolerance, we use the same networks as before, but this time we're only computing routes towards a single destination, but we assume that there can be links that have failed and cannot be used to route traffic. Usually, to this day, one will have to use an SMT-based verifier to exhaustively answer what-if questions, such as what happens if links can fail. There's no way a simulator will be able to answer these questions by enabling triangle combinations, because we're talking about networks that have thousands of links. The problem, though, is that even though SMT verifiers were designed to tackle such questions, they do not scale either, especially when it comes to larger networks. In these examples, the SMT-based approaches failed to produce an answer within 30 minutes, and I'm confident in saying that even if we had waited 30 hours, not much would have changed. Maybe the smallest network with one link failure would have been verified, but in general, it's a SAT problem is an exponential problem, and after a certain network size, it's just pointless to expect an answer from the SMT solver. On the other hand, using multi-terminal BDDs to leverage symmetries in the failure scenarios, our simulator can analyze most of these networks in a matter of seconds. And the only case where it takes a little over a minute is when considering what happens when there are up to 3 link failures for a network that has almost 22,000 links. Of course, these networks are very symmetric and this helps our analysis, but you can imagine a scenario where a misconfiguration will not allow you to use backup paths under certain failures, and we did not have a general way to verify the absence of such misconfigurations. As I'm wrapping up this talk, I would like to go back to the point of simplifying the research cycle for new network analysis. I think that there is no better demonstration that we achieved this goal than an analysis that successfully tackles one of the most challenging problems in control plane verification, like fault tolerance. And despite that fact, it took roughly 5 minutes to go from inception to the actual implementation and to running the analysis to see if it works in practice. In fact, here's the code that implements the analysis. It's literally 5 lines. I could walk you through it right now, but I'll keep this short and refer you to the paper instead. To summarize, I want to say that network misconfigurations are still a big problem for the networking industry, and developing static analysis to mitigate the issue is difficult for a number of reasons, one key reason being the lack of abstractions in configuration languages. In this paper, we developed MV, an intermediate language that aims to simplify the development process of new network analysis. And we also provide an automated translation from a small but practical subset of router configurations to MV. And finally, we showed how you can leverage the design of the language to develop a number of high-performing network analysis. That concludes my talk. I want to thank you for your time, and we're looking forward to your questions.